Hi, my name is Octavian, and it's 12 sharp. And you know what time it is? Lab time. So today I would like to present some properties of the iron metal, which can have, depending on the compounds, the oxidation state +2 or +3. So the iron metal has strong properties of a reductant metal, because I bet that anybody of you have seen how a piece of metal rusts. It's nothing else, just oxidation of the metal. So the iron undergoes through the process of corrosion only if there is present water, oxygen, and some additional air moisture. In this video, I will present you as well as the reductant properties of the iron, as the oxidative properties and its compounds. So from the beginning, I need some steel wool, which cannot be found in my country, but luckily for me, I have ordered it online and I have bought it from Great Britain. There is like a steel sponge, it's sold like a steel sponge in every other household products shop. The experiment is based on the process of iron burning, which have the shape of thin metal fibers. So, okay, I light up the iron and let's see. Wow! Incredible. I would stare at that for an eternity. Amazing. So what is really happening at the molecular level? The answer to that I can figure out in these equations. So, iron in the solid form plus oxygen gas equals to iron oxide 2, and the enthalpy of formation is equal to 264 into 8 kilojoules per mole. Okay, so this one is black. This oxide is black. Then this process is, we can see that it's 1/2 of the oxygen, so it's in insufficiency of oxygen. Okay, the redox equation should be 0, 0, plus 2, minus 2. Okay, so the iron from the 0 changed into the iron with 2 plus. So it needs to give 2 electrons, and the oxygen 1/2. Oxygen to 0 changes to oxygen minus 2. So in order for that to happen, we need to additionate 2 electrons. The iron was in the initial was a reductant and became an oxidant. And in the initial form, the oxygen was an oxidant and became a reductant. So the process for the iron, for the changing the degrees of the iron, is oxidation states is the oxidation process, and for the oxygen it's a reduction process. The lowest multiple, a common multiple, is 2. 2 divided by 2 is 1, and 2 divided by 2 is 1. Okay, so we just need to put this 1/2 of oxygen here, and the equation is balanced. Okay, this is the first equation. Moving on to the second. Iron plus oxygen, iron 2, oxygen 3. Okay, so here is solid, here is solid, here is gas, and this one is solid. The enthalpy of formation is equal to 824 and 2 kilojoules per mole. Okay, so it's an exothermic equation. This one is an exothermic too, because we have seen that the sparks on the iron have appeared when the reaction started to happen. Okay, so the iron from 0 and oxygen from 0 turned into the iron plus 3 ions, and oxygen minus 2. Minus 2 multiplied by 3, it's minus 6, and divided by 2, it's minus 3. So we need plus 3 in order to balance these two. Okay, so iron changed into iron plus 3 ion, 0. In order for that to happen, he needs to give 3 electrons. And the oxygen, okay, it's 2 iron, it's 2 here and 2 here. Then it's not quite simple. He needs to give 6 electrons. 6 electrons, okay. And then here is 2, here is 3, 3 other 2. 2, 3, O minus 2. So in order to that, the oxygen needs the addition of 6 more electrons. So let's write that. As well as in the first equation, the I was a reductant. It became an oxidant. Okay, and the oxygen was an oxidant and became a reductant. This one is called the oxidation process, and this one is a reduction process. Okay, so the common multiple, lowest common multiple is 6. 6 divided by 6 is 1. 1 and 6. Let's write this properly. 1. 6 divided by 6, it's again 1. Okay, so if it's 1 and 1, we need to put these numbers to all of this to balance the equation. So we have 2 here, we do not have here, it's 2. And we have 3 over 2 here, and here we have 3. So the equation is balanced. But the fact is, in the reality, we obtain a different iron oxide, like a combination between those two. So we can write a summary for all of this, and this is in sufficiency, in excess. Oxygen. Okay, so the overall reaction should be iron plus, I wanted to mention that this one is like orange color or a brick color. It's orange And the last one, iron plus O2 is equal to 2, gives us iron 3O4 oxide. That is nothing else but a combination of iron O and iron 2O3. And of course the enthalpy of formation is lower than 0. Okay, let's equal this one. So we can see that iron here has 0, oxygen has 0, oxygen here has -2, so -2 multiplied by 4, it's -8. But the thing is, -8 divided by 3 is not a whole number, so we should write that down, that the oxidation state of the iron is +8/3. How strange would that will that sound, but it's what it is. Okay, let's examine this redox equation. So iron changes to iron 8 plus 8/3, and this is 0, but what's the point? It's 3 here and 3 here. So the 3 of this one multiplied by this one will cancel each other out, so it will be 8 electrons. We need to give 8 electrons minus 8 electrons. Okay, and oxygen, it's 2. We have here 4 oxygen minus 2, it's 0 here. Okay, and we need 2 more, so the overall we will need to add 8 electrons more. Okay, 8 and 8. So the iron should be a reductant, oxidant in this final state. The oxygen should be an oxidant, and in the final state a reductant. It's again an oxidation process. Oxidation process, and it's a reduction process. The lowest common multiple is 8. 8 divided by 8, it's 1. 8 divided by 8, it's 1. So we need to respect these ones. Okay, so 3 we have here and 4 we have here. We need just to figure out this one. So we need 3 here and we need 2 here. And the equation is balanced. Proceeding to the next experiment. Now I'm going to need the iron 3 oxide, which is iron 2O3. And why I have mentioned it on the table, it was orange color. You can see that. It's like an orangish color. Okay. And we are going to need some aluminum powder. Okay, so I am going to need the aluminum powder and the iron oxide in a ratio of 1 to 3. So I'm going to take 12.5 grams of aluminum powder and almost 37.5 grams of iron oxide. So in the total I'll have a mass of 50 grams of the mixture. I'll mix them both, and this mixture is known as a thermite reaction. We are going to mix them properly and put the mixture into an iron pan with a thick bottom, because I'll explain why. It's an interesting process. Okay, so let's mix this. This will be a long process of mixing it properly, but I guarantee you it will be awesome. Okay, I'm done. So I'll put it right here, like so. And the next thing we are going to do is to light it up, this mixture with the burner. Okay, so I'm going to lit it up. So let's see what happens. Okay, let's see. So I will add more aluminum and that should help. Okay, so let's see one more time. Yeah, it won't gonna work. Okay, let's add more aluminum and that should help out. We won't mix it because we need just for the aluminum to ignite, and then it will ignite the iron oxide too. More iron oxide. Okay, we will stop here. So what has just really happened? Let me firstly clean this. So in industry, this reaction is called aluminothermic reaction, where aluminum and other metals react at high temperatures. So aluminum is of his role of the reductant. He reduces the metal from its oxide, becoming the aluminum oxide and the metal respectively. In this case, the aluminum can substitute only the metals that have a higher standard electrode potential than itself. After this reaction, the metal then is separated from the aluminum oxide and then purified. So the standard electrode potential for the iron, E for the iron 3 plus, it's E0 or iron, is equal to minus 0.44 volts, where the aluminum one, E0 of the aluminum plus 3, or aluminum, is equal to minus 1 and 66 volts. So yeah, we can definitely see that aluminum has a lower electrode potential than the iron one. Okay, so the equation that described that process was iron 2O3 plus aluminum metal. Okay, it's solid and solid again, is equal to iron plus aluminum 2O3, which both are solid as well. Okay, of course, the enthalpy of formation is equal to 851.5 kilojoules Okay, it's a lot of energy, it's a lot of heat. And let's see the redox equation. So it is at a high temperature, of course, to ignite the equation. Then iron from the +3 ion and aluminum from the 0 changed to iron 0 and aluminum +3. Okay, so iron from the +3 to iron from the +3. It changed to iron for 0 with 0. This means it should have gained 6 electrons, plus 6 electrons minus, and the aluminum with 0 changes into the oxidation state of aluminum +3. And then here is 2, so we put 2 here and 2 here, and it needs to give 3 electrons, so minus 6 electrons, because there are 2. We need to give 2 to multiply by 3, it's 6. Okay, so let's write down that the iron in this case is an oxidant, and it became a reductant. And the aluminum was a reductant, of course, because it reduces the iron, and it became an oxidant. Okay, so then it's called a reduction process and an oxidation process. The lowest multiple, a common multiple, is 6. So 6 divided by 6 is 1, and 6 divided by 6 it's 1. So we should just see those, and the equation should be balanced. Okay, so we have 2 here from the iron, and 1 iron, so we'll add here 2. And the aluminum, we have 1 here and 2 here, so we add here 2. And the equation is indeed balanced. So in this way we can conclude that the iron ion, that is +3, was reduced to its metallic form by the aluminum, and this process is called aluminothermic reaction. So why have I used a thick bottom pan? It's because of the fact that the process should have gave more heat, an enormous amount of heat, like you see in the equation, because the enthalpy of formation is very high indeed. So this amount of heat can result in melting the pan. So that's why I used small proportions, and I used a thick pan in order not to melt my pan down. But of course the overall reaction wasn't so successful. It had only some sparks. It didn't have the expected result. So it can be caused by the fact that I store the aluminum into just a plastic bottle, and it can easily contact with the moisture. So in order to that, it makes the oxidative stratus, and it prevents for the next oxidation of the metal. So the overall reaction didn't happen because I had mostly aluminum oxide there, not the aluminum itself. So yeah, but thanks for watching and have a nice day indeed.